Jack is certainly one of, if not the foremost person in high-performance computing today, and has been for a number of years. And I've known Jack for several years. He gave a distinguished lecture here, I don't know, 5 or 6 or...
Probably longer. 2004, I'm remembering.
2004,
I don't
wow.
know.
It's been a while. And things have changed, as you will see, on the high-performance computing front since then. Jack's a member of the National Academy of Engineering, and he's a fellow of just about every society on Earth, and he has many, many awards.
And a jolly good fellow.
So, and I'm sure you would rather hear him talk about his work. So please join me in welcoming Jack Dongarra.
Thanks, Chris, for that very kind introduction. I'd like to keep things informal. So if you have a question during the talk, ask the question when you have it, rather than waiting to the end. I think it'll make it more fun for you and for me, I guess. So I'm at the University of Tennessee in Knoxville, and I also have an appointment at Oak Ridge National Lab. Oak Ridge is about maybe 40 miles from Knoxville. I work there. I also have an appointment at the University of Manchester. That's about 4,000 miles from Knoxville, and I don't go there every day, but I do go there occasionally. And we're going to talk about high-performance computing, and I want to look at it, maybe where we've been and perhaps where we're going, and look at some of the challenges for software and algorithms as we go there. Okay, so to start off, let me say we're going to look at high-performance computing through the eyes of this data that we've collected. So back in 1993, Hans Moyer approached me and asked if we could put together a list of the fastest computers. I had a benchmark. He had an idea, and we put together those two and came up with this thing called the Top 500 list. So this is a list of the 500 fastest computers. And we're talking about scientific things, so we're going to measure fastness in terms of floating point operations. And whenever I talk about floating point operations, I mean adds or multiplies of 64-bit operands. So that's really what a flop is in this context. And we have a benchmark for better or worse, called, for better or worse, we're going to use this benchmark to measure, to rank the computers. The benchmark is called the LINPACK benchmark. LINPACK, some of you may know it as a package of mathematical software. It's taken off, this benchmark thing has a life of its own now, and the benchmark is to solve this matrix problem, AX equal B. Solve a dense matrix problem on your computer, and solve it using the best implementation you can for Gauss elimination of partial pivoting. That's sort of one of the ground rules for it. 64-bit floating point arithmetic. You have to get the answer to a prescribed accuracy. We can talk about that if you'd like, so you can't guess the answer. And you have to solve it with my matrix. So I'm going to give you a matrix. You're going to implement how you decompose it for partial pivoting as fast as you can on your computer and report the results. And the way to think of this is, if I solve this problem, and we're looking at a rate of execution, not time, rate. So flops per second is what we're going to. So there's n cubed. It's 2/3 n cubed operations to do that, divided by the time, and that gives the rate that we're going to be looking at. And if you think about, if you increase the size of the matrix, it's a square matrix, solving that matrix, and you think about what happens to the rate, typically the rate goes up until you reach some asymptotic point. And you want to catch the asymptotic point. You want to look at the best performance on your machine. Right? So you want to solve a big problem. Typically what happens is you fill your machine up with this matrix and you solve it. And then you report the time and you compute the rate of execution. We also look to ensure that you got the right answer. Okay, so this list of the 500 fastest computers gets updated twice a year. It's updated in November at the supercomputing meeting, which will be next time here in Salt Lake City. Where's it going to be?
The Convention Center. The Salt Palace, yeah. Okay,
and then it's also updated in June at the meeting in Germany, in Hamburg. There's a website that contains all the information. So we've been doing this since 1993, collecting this data, looking at the 500 fastest computers. And this is a snapshot, if you will, of supercomputing. So it starts in 1993 and goes to November of 2011. That was the last time we measured the performance, we came out with a report. The way to read this is the green line here is charting number 1. So that's the fastest computer. Fastest computer today is at 10.5 petaflops. 10.5 times 10 to the 15 operations per second. That's the rate that they solved that problem, right? So 10 times 10 to the 15 operations per second. 51 teraflops is the guy at the bottom of the list. That's the guy that just made it on the list. That's number 500, right? So that sort of brackets, if you will, high performance computing. This red line here is the sum of the 500 computers. So that's an artificial number. That's a spreadsheet calculation, right? That's an Excel spreadsheet. So 74 petaflops is the aggregate sum of the 500 computers today. And you can see where things have been, right? So how things have tracked over time. There's sort of a straight line here for number 500 machine, straight line here for the sum, but we see a jagged line for number 1. Well, sometimes a new machine is introduced which is a lot faster than the previous guy, and that causes this big bump to go up, right? So we see that big bump. There's a big bump here, there's another one here, a few here, one here. When much bigger machines were introduced to boost things up. We'll take a look at this machine in some specifics. The slope of the line, what's the slope of the line? What should it be? Something like Moore's Law. Moore's Law says something's going to double every maybe 18 to 24 months. So the slope here is doubling every 14 months. So why would it double 14 months? What's sort of accelerating Moore's Law? Parallel processing. So every time the list comes out, more and more processors are used, and that's sort of giving it some kind of boost associated with it. It's sort of stunning here. This guy at the bottom of the list, that was equal to the sum of all the machines not too long ago. So back here in 1998, that was the sum of all the computers. So this exponential thing is really quite stunning. And the thing to realize is going from number 1 to falling off the list takes about 6 to 8 years. Right? So these machines at number 1 typically cost $200 million. Right? That's the cost of the machine. In 6 to 8 years, you want to get rid of it because it's not a supercomputer anymore, right? So you've got to get a new one. So you got to do another investment in this thing. So really quite stunning changes with exponentials. Okay, so my laptop. So it's a pretty impressive machine. Dual core, Intel processor. I can run the benchmark on my laptop. And when I run the benchmark, I get 12 gigaflops. That's stunning. This is a laptop I use to give talks and read mail. That's what I use it for. And I get 12 gigaflops out of that. Not too long ago, that would have been a supercomputer. Right? That's a stunning thing. Exponentials are just incredible in terms of what's going on here. I know something about exponentials, but when it touches stuff I use, I have a hard time really projecting where this is going. Okay, so my iPhone, I can run the benchmark. There's an app for that. You can download it. You can download the Linpack app. And I get 1 gigaflop out of this thing. 1 gigaflop. I don't know if you're old enough to know this, but a Cray 2 was 1 gigaflop of performance, a Cray 2. And I carried that around on my waist. That's just an incredible thing. So that would have been a supercomputer not too long ago. So that, again, stunning advances going on here. It's just incredible when you think about it. And you wonder, what's that power going to be used for in devices that we use on an hourly basis. Okay, so just so we're all in the same framework here about how supercomputers are built, here's a typical supercomputer. This is how you build them. There's a multi-core chip. This chip here has 6 cores. My model down here has 4 cores, so bear with me. So it's a chip, it's a socket, and it has multiple cores. Think of it as multiple processors, right? So we're all on the same page. And the way this works in parallel, I'm going to have these guys cooperate. So information, has got to be shared between these cores. If you think about doing that somehow on a machine like my laptop here, I can coordinate those computations very easily across that one chip. Maybe using shared memory is the simplest way to deal with that from a programming standpoint. And we're going to take that chip and put it on a board. So we're going to have a node, and that node is going to be consist of multiple chips on that board. And today the way we think of organizing things, we might think of attaching something else to that chip. So the GPU is attached to a chip, and we may have multiple GPUs, we have multiple things going on here, but there's an association between a chip and a GPU. The GPU is there to accelerate what the CPU can do. The CPU is thought of as a very heavyweight, general purpose thing. The GPU is more specialized, more lightweight in some sense. And information is going to flow between this core through the chip, through the node board, down to another core to coordinate the computation. We're going to do something in parallel. And again, the programming paradigm may be shared memory. Maybe a shared memory programming paradigm. And we're going to take those boards and fill up a cabinet. So we're going to think about shoving boards into a cabinet now. And coordination is going to take place between cores on a chip. It may take place between cores on a node board, and it may take place within a cabinet. And perhaps in a cabinet, the programming paradigm that we use will be a message passing one. We're going to send information explicitly using send and receive, using MPI as the standard interface for doing that. And we're not going to stop there. We're going to take those cabinets and fill up a room. Fill up a room with a lot of cabinets and have a switch that controls how information flows around there. So that's a very typical high-performance machine today. The machine in Japan, the #1 machine, looks just like that. No GPUs. I've taken out the GPUs. And it looks very similar to this configuration where we have node boards made up of multi-core processors, those boards stuck in a cabinet, and a room then is filled up with cabinets, 800 cabinets or more in a room. Very, very large configuration. Okay, so if we take a look at the 10 fastest computers, here's that list. Here's #1. It's a machine in Japan. It's at Riken. It's in Kobe. And it's composed of Fujitsu processors. Fujitsu has a chip, which is a SPARC architecture. So it's using the SPARC Sun's instruction set is the implementation. They've augmented that with some instructions which do vector operations, short vector operations very fast. It's not a vector machine, but short vector operations, similar to SSE2 instructions, if you will, on the Intel machine. And that machine has 7,000 cores in it. 700,000 cores in it, sorry. 700,000 cores in it, about 250,000 cores inside this machine. Big machine. And they achieved 10 petaflops. 10.5 petaflops was the achieved performance. And that's 93% of the theoretical peak. So theoretical peak is a number you do, is a calculation you do on with paper and pencil. What's the cycle time? How many operations complete per cycle? How many cores do you have in your machine? That's the theoretical peak. And then what they achieve is the benchmark result. And they get 93% of that. That's very impressive. That's a stunning number. It's one of the highest numbers I've ever seen. I thought they cheated when I first saw it. And I said, explain to me how you got 93%. And they did, and I believe it. The #2 machine is a machine in China, the Tianhu 1A. It's at the National University for Defense Technology. They're the guys who composed the machine. The machine is composed of Western parts, Intel plus NVIDIA plus an interconnect, which they did. So they made their own interconnect. They're not using InfiniBand. They decided to design their own interconnect with their own chips. Right? So it's a custom-made interconnect, just as the Fujitsu machine is a custom interconnect. Right? The Chinese interconnect is slightly faster than InfiniBand, about the same latency measured through MPI. And that machine has 186,000 cores. You have to be a little bit careful. This is a composite machine, Intel plus NVIDIA, hybrid. And we have to be careful how we count cores. It's not CUDA cores I'm counting, it's the equivalent number of cores. And we can talk about that later to get how that computation is arrived at. But it's 186,000, what I would call cores. And they achieved 2.57 petaflops, which is 55% of the theoretical peak. So that percent, 55%, I would say is low. This is a problem which should get very high performance on these computers. That's getting about half. Using GPUs, that's a very common story for this particular problem. Getting about half of the theoretical peak. So it's a warning. There's something going on with GPUs where you're not able to extract very high, the highest levels of performance, the peak performance. And we'll talk about why that is in a bit. And you can go down and listen to the machine we have at Oak Ridge National Lab. It's made by Cray. It uses AMD plus a custom interconnect. Cray's secret sauce is their interconnect. It's 250,000 cores in the machine, AMD processors. 1.76 petaflops, 75%. 75% is a very common number for efficiency for machines which are of this nature, of a commodity processor with a high performance interconnect associated with them. Okay, we can scan down the list and look at the other guys. There's 2 machines in China. Both of those machines are GPU based. One has custom interconnect, the other one's using InfiniBand. There's 2 machines in Japan, both. The second one is again, a hybrid machine, Intel plus NVIDIA plus InfiniBand. Again, you see that number, 52% of the theoretical peak. Machine in France made by Bull, which is Intel plus InfiniBand. They're the integrators. They've integrated those components. And a few other machines in the US along the way. All the machines in the top 10 over a petaflop of computing power. And again, we see this rather striking difference between the efficiencies of these machines. The other thing to realize are these machines are big machines. And big machines, they have lots of cores, lots of processing power, requires lots of power, electrical power. Right? So if you take a look at the power consumption for these machines, it's measured in megawatts. Right? So the machine in Japan is 12.7 megawatts of power. 12.7 megawatts. So what's a megawatt? 1 megawatt per year, where I am in Tennessee, where we have TVA, is about $1 million. $1 million per megawatt to turn it on per year. So about $12.7 million that machine would cost just to have the lights go on. Well, it's a little bit confusing because this is actually under load. This is running the benchmark. That's when we get the power requirements. So running the benchmark, not running it, having the machine idle is a little bit less power. Right? And you can look at the numbers here. Again, all over a megawatt of power for these machines, very hot machines. And this is the efficiency. What's the flops per watt? Right? So you want that as high as possible. You want to get as many flops per watt. And when you look down the list here, the guys that have the highest numbers are the GPU guys. The machines that have GPUs typically have pretty good numbers. This is one of the best ones here. It's the machine in Tokyo Institute of Technology. And again, it's Intel plus NVIDIA. The Fujitsu machine also has very impressive efficiency. Very well balanced machine. The Fujitsu machine is designed for high performance computing. The processor was designed for high performance computing. The interconnect was designed for high performance computing. The other machines here are using commodity processors for the most part. And those were not necessarily high performance computing components. Right? Some machines are using InfiniBand, which is high performance enough. But that's not the way all of the machines on the top 500 exist. I stuck down here the guy at the bottom of the list. This is the guy that just made it on the list, machine number 500. It's using Intel parts plus gigabit Ethernet. Gig-E for the interconnect. You know, that's a very poor interconnect if you're building a high-performance machine. The bandwidth and latency are going to suffer, but it's low cost. So people are trying to lowball high-performance computing in some sense by buying an inexpensive interconnect, and their performance is going to suffer. They achieve 53% of the theoretical peak. And that's a direct result of that interconnect being the way it is. Okay, so that's just top 10 machines. So here's a quiz question. How many of the top 500 machines, how many of the 500 machines on the list today use GPUs? So we'll come back to that question. Notice a number of guys here using GPUs, NVIDIA parts are used. This machine is using the IBM Cell processor. IBM Cell is the processor that was used here is similar to the processor that's in the Sony PlayStation. Right? DOE gave IBM, Sony, Toshiba some money and said, improve the double precision floating point of that chip and we'll build a machine and maybe sell these things to a wider market. So they did that. They received money from the Department of Energy. They modified the chip. They produced this machine and IBM says, nah, we're not going to do that. So that's no longer a problem. Okay, this is the number one machine. This is the machine in Japan. Just quickly, it's built on an 8-core chip. The chip is 2 gigahertz, relatively modest cycle time. 128 gigaflops for that chip, the theoretical peak. It's using Spark plus these extensions. It has some cache, it's got some power requirements, it's got a pretty impressive memory bandwidth on the chip itself to its memory. This chip is used on a node board. So the way this machine is composed is there's one chip on a node. Within a board, they place 4 of these nodes on it, and then they place this system board in a rack, and then they fill up a room with 800 racks. And again, they got 700,000 cores on this machine. The impressive thing about this machine is, you can't see it here, but the K computer, if you look at the performance, it's equivalent to summing up the next, I can't see it either, the next 7 machines. So if you add up the performance of 2 through 8, that number there is still less than what the K computer is. Okay, so that's an impressive thing. And between number 1 and number 2, there's a factor of 2.5. So a big jump in performance with the K computer. Right, Japan made a big investment. Rumors are that machine cost $1 billion. $1 billion. That includes all the development and everything else that went into it. Very expensive machine, right? They're very proud of this machine.
Is this the only chilled water machine in that list?
No, there's other chilled water machines. Okay. Yeah, that's right. So the Cray machine we have is sort of chilled water as well. Okay, so to, let's see, what's the point here? I wanted to say something about this. Oh yeah, to run the benchmark, it took 29 hours, 29 and a half hours to run the benchmark. They solved a very large problem. They ran it for 29 hours. The stunning thing is the machine stayed up for 29 and a half hours. That's a stunning thing. This is a new machine. They just brought it in, connected it, ran the benchmark because they wanted to be number 1. Ran for 29 hours, no problem. Right? So I went up to the Japanese. I said, "What's the mean time to failure of the machine?" And the engineers went off on the side and discussed it, and they said, "We don't know." What do you mean you don't know? I said, "We've only had 1 failure. So we don't know what the mean time is between the
So, how much time does it take for it to use the megawatts? Is that every hour it uses that?
So what's the instantaneous rate of power consumption? I guess is the it's measured in 12 megawatt hours. I don't know how these numbers are better are computed. So China is very aggressive in terms of high performance computing. In the year 2000, they had no machines on the top 500, zero machines. Today they have 75. So they're number 2 in terms of high performance computing power, in some sense. Right, they have 75 machines on the top 500. The US has 263, and then you can see Japan and the other guys here. They have 6 petaflop machines in China. 6 petaflop machines. 4 of them are based on GPUs, NVIDIA parts, and Intel processors. These are big machines, of course. So we see a tremendous investment going on in China in high performance computing. In the U.S., there are 5 planned petaflop machines coming. There are 4 that will be deployed this year, is the thinking. So there's a machine at Oak Ridge called Titan, which is being put in place. That's going to be a hybrid machine based on AMD plus NVIDIA parts. Part of the machine will be built like that. How big the machine will be, a hybrid, will just be determined by the amount of money they have. There's a machine being deployed at Lawrence Livermore National Lab based on IBM's Blue Gene architecture. It's a Blue Gene Q. So both of these machines are at 20 petaflops. Is the peak performance for those machines, 20 petaflops. There's a machine going in Argonne National Lab at 10 petaflops, also a Blue Gene. There's a machine going in at the University of Illinois. That's going to be a Cray computer. Right? At one point it was going to be IBM, and then IBM said, we're not going to build that. So they received money from NSF, and they said, we can't build the machine, we're going to lose too much money. So University of Illinois scrambled and arranged a deal with Cray to deploy a hybrid system at over 10 petaflops. It'll be 11.5 is the peak performance. And then there's a machine that NSF is funding that's going to be put in place at the University of Texas, which will be a Dell manufactured machine, Intel parts, using the Mike architecture. That's Mike is their next generation graphics stuff.
Do you have a sense of the downgrading performance of the switch from IBM to Cray as a result of Blue Wires?
Yeah, so we never really saw the performance. It was never really reported.
Is there an anticipated performance that you?
Oh, so from Cray.
Yeah.
So yeah, we know that very specifically what the Cray performance is. I can't remember the numbers. I don't know how to compare it. I don't know what the IBM thing is.
The IBM numbers were aiming for about 10 petaflops, but they were also aiming for 1 petaflop sustained.
There was so the claim in Illinois is that they wanted a 1 petaflop sustained machine for applications. They didn't care about benchmarks so much. They didn't care about benchmarks. That was their standpoint. And the Illinois machine will be used primarily. The plan is they'll use the whole machine for an application rather than to split it up into smaller pieces for many users simultaneously. They would like to focus on the small number of users getting access to a larger chunk of the machine. Okay, so those machines are coming from in the US. Okay, so there's a lot of hype about GPUs. So here's a cartoon that sort of describes how things are connected. And the way you should think of this is there's a host processor, commodity processor usually, and then a GPU. And this cartoon has an Intel 8-core thing which has 96 gigaflops theoretical peak performance, and it's connected to an NVIDIA Fermi processor which has 515 gigaflops theoretical peak performance. So they're connected using a DMA connection. So electrically, that's realized using a PCI Express bus. And PCI Express, the connection here is measured in terms of the speed or bandwidth associated with it is 64 gigabits per second, or 1 gigaword per second. 1 gigaword, that's the number you should have in mind, 64-bit words. And remember, this guy here is at 515 gigaflops. That's its rate of execution. So that says moving data across this link, and the way this works is you move data from the host over to the device memory, and then you do the computation on the device, and then you move it back to the host. That's the flow of information. So you start the computation here, you move data over here, you make a call which says, execute this on the data I just moved over there, the data gets the operations take place over here, and then you say, bring the data back to the host. So that's sort of the standard mode. And this link here is going to kill you, right? If you just move one piece of data, do an operation, and move it back, you're going to die. You're going to die moving the data. It's 1 gigaword per second. This is a half a teraflop of floating point computing power over there. You've got to have a lot of work to do over there on the data for it to make sense. Remember I said 50% theoretical peak? That's why you're getting 50% theoretical peak, because of that poor link between those two devices. And that becomes the strangle point, if you will, for a hybrid architecture that's of this kind of design. Okay, back to the quiz question. How many machines on the top 500 use GPUs today? How many say half of the machines? No, there's one guy who says half. That's wrong. How many say 10% of the machines? 10%. So 50 machines. Okay, so the answer is today 39 machines. 39 machines of the 500 use GPUs. So is that big or small? It's growing. It's growing. And this is sort of the how things have grown. So back in 2006, there was a company called ClearSpeed that made accelerators, and they had a few machines. And then IBM had their cell processor, and then ATI through AMD has a device, a GPU, they have a GPU. And NVIDIA is certainly saturating the market there, so to speak. There's 20 of these things in the US, 5 in China, 3 in Japan, and so on and so forth. So it is increasing, and I would expect that number to increase as things roll out. This thing with GPUs, we've seen this before. This is not new, right? So I've been around long enough to see this story be replayed. So floating point systems in the old days, in 1976, had something called the FPS 164. It was an attached processor. It attached to a mainframe, and it was connected through a link. You pass data over Floating point operations would take place over there, and he'd bring them back to the mainframe. That was a device that FPS made, and they were able to sustain a business up to a point. Intel had a math coprocessor. We forget that the floating point was not always on the chip. They had another chip next to it, which did floating point operations, and you moved data over there, it did the operation, moved it back to the other part. YTech had a chip which connected to Sun workstations, I remember it, which would do offload floating point computing power. So this is not a new story. We've seen this before, and floating point became embedded in the chip. In the Intel case, it became embedded in the chip. Made some of these things here superficial, they went out of business. And we're going to see that same kind of story play out over the near future. With the FPS machine, it was connected perhaps to a VAX computer, a DEC VAX computer. The FPS machine had 11 megaflops, that was its theoretical peak performance, and a transfer rate of 44 megabytes per second, and that gave a flop rate of 1 flop for 4 bytes. That was sort of the trade-off between moving data and doing the computation over in the accelerator. And today, with the Fermi board connected through the PCI Express to a host, we've got about 500 gigaflops. The transfer rate is 8 gigabytes per second, and that leads to a 62 flops per byte transfer rate. So you see the transfer rate's gotten much worse in this case here. You have to do more operations over on the accelerator to make things work. Essentially, floating point operations are cheap. And today we over-provision for the floating point operations, and we have to be concerned about data movement. We have to be concerned about how effectively we can move data around inside the machine. Future systems, we're going to see more integration along these lines, putting the floating point capability inside of the main processor, let's call it. Intel has their like architecture, which is in this direction. Putting x86, lightweight x86 cores on the chip itself. AMD has something called Fusion, which is doing this today, and NVIDIA has something which is projected to do this in the near future, basing their architecture on ARM. Right? So what's ARM? Well, ARM's the processor which has the most processors around today. ARM is the processor architecture that's in our cell phones. And so it's thought it was a lightweight, low power, capability device, and NVIDIA is going to build something around that. And typically, the kind of thing we would project, today we have a situation where our processors are what I'll call commodity, heavyweight, large cores. In the future, we would see chips manufactured which would have a trade-off, perhaps, of these heavyweight and lightweight cores. With the lightweight cores were these accelerator things capable of doing floating point operations very fast, put on the chip itself to minimize that communication issue of passing information along a slow link, and manufacturers would sort of dial up how they were going to produce these chips. Some chips for the home market would have more heavyweight cores. For gaming, of course, they would have more lightweight, graphical kind of cores, and scientific would have some mix of those associated with those chips. The other issue is about getting data into a chip. The data in a chip today is, we think about the information coming in on the perimeter of the chip through the pins. The memory's out there and data comes in on the pins. As the processing power increases of the chip, there's more data demand, and it can't be satisfied by that perimeter of pins. So the structure that people are working on is looking at stacking memory, three-dimensional memory on top of the chip, where data would be able to flow vertically into the chip rather than have data come in only from the edges of the chip itself, allowing for more bandwidth and allowing for a better trade-off between data flow and the floating point capability. If we take a look at the cost of moving data and the cost of doing floating point operations, today it has the following effect. A double precision floating point multiply add instruction takes about 100 picojoules to do. That's the energy cost associated with doing that operation when the results are in registers. And to move data from memory, outside memory, primary memory, into the part of the machine where the operations are going to be performed takes about 4,800 picojoules. So the cost of moving data is much greater than the cost of doing the floating point operations today. In the future, things are going to improve. That's the good news. Floating point operations go down to 10 picojoules, so you get an order of magnitude reduction there. The bad news is, well, the good news is we're going to get a reduction in terms of the movement of data, but it's not going to keep pace with that reduction that we see, order of magnitude reduction. It's only going to go down, the data movement's only going to go down to about 2,000 picojoules. So it's still going to be relatively high, and the ratio is going to be worse in that case. So data movement's going to be critical, and in terms of designing software, we really have to work towards minimizing data movement in our operations. The machines are over-provisioned for floating point. Data movement's going to be critical. You have to focus on looking at ways in which to minimize data movement. In the US and beyond, there's been a major effort to understand what the needs are for computational scientists. So DOE has been instrumental in bringing together different communities, computational science communities, and asking questions about what are your limitations today? What do you need to advance your science? What are the important problems and what's needed to make breakthroughs in those problems? And all of those domain science workshops resulted in we need more computing power. We need exascale computing. Right? We need to push forward where we are today and have more computing deployed. This is a list of workshop reports that have been produced over the last few years, each of which discussed this issue and each of which came to that conclusion. So the DOE has built up what I'll call a science case for exascale computing. Right? So it's not a technology push which is driving us to exascale. It's coming from the science domains. They're requiring exascale computing, and that's where things are presumably going. This is the top 500 numbers that we looked at before. If we do an extrapolation of those numbers, and it's been a pretty straight line so far for number one machine, it says that we get to exascale roughly in 2020 time period. So if things are on track, and they've been on track for a while, I would have to guess that things are going to continue along those lines, as long as technology improves. We should be at exascale roughly in the 2020 time frame. So about 8 years from today, we'll see exascale-based computing is the projection. And if we take a look at exascale and look at where we are today and look at what's needed to get there, we end up with the following kind of analysis. This is the specs for the Japanese K computer this past year when it came out. And the question is, what do we need to go to exascale? The Department of Energy and others have put limitations on that design. And the limitations are you can spend no more than $200 million on the machine. So it caps the cost of the machine. And they also say, look, you can't go beyond 20 megawatts. That's your limit, that's your power budget for this machine. $200 million and 20 megawatts is the constraints on the problem. And they say, okay, design an exascale machine with that. So here's a design for exascale based on those two constraints. Given $200 million, you're going to spend half of the money on memory. So you're going to dump $100 million into memory. The semiconductor guys have a very good roadmap of where memory is going, and they can project pretty closely how much $200 million will buy at that time period. And this is what the machine looks like in 2019. So we get to an exascale, we get to 20 megawatts. The machine will have between 32 and 64 petabytes of memory. The node performance has a certain rate, up to 15 teraflops. The memory, the bandwidth of a node, data moving within a node, is 2 to 4 terabytes per second. The concurrency at a node is measured in terms of thousands or tens of thousands of things, threads of execution. The bandwidth between nodes, message passing, is measured in terms of 200 to 400 gigabytes per second. The concurrency, the threads of execution, is measured in a billion. So you have to think about programming this machine. You have to manage, coordinate, orchestrate a billion threads of execution only. And the mean time between interrupt is measured in terms of maybe 24 hours. So that brings about a number of very different issues in terms of where we are today and where the machine will be in 2019. So we get 2 orders of magnitude in terms of performance. We're at 10 petaflops, we're going to an exascale, 10 to the 18. We're only going to get one order of magnitude in terms of memory. One order of magnitude in terms of memory. We're going to get one order of magnitude in terms of the interconnect between nodes. We get 3 orders of magnitude in terms of the parallelism we have to manage. And we get a decrease of an order of magnitude in terms of the reliability of our system. So the memory constraints say something about scalability. Today our machines exhibit weak scalability. So we think about as the machine grows, we can grow the size of our problem, and we can scale the problem up with the machine. So this says we probably won't be able to do that. We won't have weak scalability associated with it. So there's some constraints in terms of the memory. The interconnect is going to be issues about message passing, concurrency, looking at a billion-way concurrency, looking at the programming models we have today, that's really going to be an issue. Today our programming model is C plus MPI. Think about programming in a billion-way parallelism with MPI, that's going to bring about some great challenges for the development. And then the mean time between interrupt is another crucial thing here. Are all coming to having major problems. So this is major changes in terms of the software and algorithms. You've got to rethink how we're doing business. Very disruptive technology, multi-core, and the things that follow from it. Data movement is very expensive. Flops are cheap. And we have to organize our operations, our algorithms, and our software to effectively deal with that. So when I think about where are the critical points from my work, we're interested in developing numerical libraries. We're interested in developing mathematical software that runs efficiently on these machines, on exascale machines. So here are the critical things that I deal with, or I want to focus on. I have to have algorithms which reduce synchronization. Billion-way parallelism, I can't do parallel processing the way I've done it. How do we do it today? We do fork-join parallelism around loops. There's a loop, a bunch of things to be done. I can do that in parallel, and I think about forking that off and then joining at the end of the loop. I can't do that. I have to have a more asynchronous way of doing the operations, doing things in independent streams, and not being constrained by that synchronization point in order to get my parallelism up there and not be constrained by that issue. And there's some ideas there that will drive us in that direction. Communication is going to be such a critical issue. We have to come up with methods which minimize the communication patterns and the communication that we undergo within our algorithms. And there's a number of, there's a body of work going on today to come up with methods which have lower bounds in terms of the communication for a given algorithm. And what we need to do is to understand those lower bounds and then implement them in algorithms and ultimately software. We want to be able to exploit mixed precision. So by that I mean we want to be able to exploit 32-bit and 64-bit operations. 32-bit operations on our commodity processors, there's a factor of 2. It's twice as fast in terms of the operations, and there's less data movement. 32-bit operands instead of 64. So we get a win in both cases. So we want to be able to extract some level of accuracy in 32-bit and then refine it with 64-bit. Think about doing part of the iteration in 32-bit arithmetic and then switch to 64 to drive the computation to convergence with the higher precision. We want to look at auto-tuning. These machines are terribly complex, and we can't expect users to turn the knobs and adjust things to get the optimum performance. You've got to build that into your software. The software has to be able to adjust itself to the underlying hardware that it's running on, the environment that it's running on. And do that, it has to be built into the software to be able to adjust to the properties that are undergoing, that are being given to it to do its computation. And fault resilience is an important aspect. We want to be able to have algorithms that can recover from failure and carry on. Today's model for fault tolerance is to do a checkpoint and then restart from the checkpoint if we fail. Some of these machines may not have disks, so there's no place to do the checkpoint. So we have to come up with methods that can effectively deal with the possibility of failure of errors occurring and recovering from those errors without losing the computation. And there's two kinds of errors. There's errors that occur from hard processor failures, and then errors that occur because maybe a bit has been flipped. I think about, so we have a number of these GPU-based machines. So there's a machine at Oak Ridge called Keeneland. It's a large GPU cluster thing. NSF funded. And if you know something about GPUs, you know that you can turn off, so the GPU has memory associated with it, and that memory is error correcting memory. But you can turn it off. You can turn off the error correcting memory. Error correcting memory says if something happens, a cosmic ray happens, it flips a bit, it's able to detect and correct 1 and 2 bit flips in a word. And if you turn off that property, all bets are off. I've got users coming to me and saying, we want to turn that off. I want to turn off error correcting memory. I say, why do you want to do that? It's 30% faster. And I get more memory. So you can see people are driven to that. And I say, well, if you turn it off, you may get the wrong answer. So I'm not going to worry about that. Okay, well then don't bother doing the computation. Here's the answer. I know what these people are thinking.
We have a user on campus who does that too.
I said, oh God, don't tell me about it. So we want to be in a position to correct for bit flips, silent errors, I'll call them, in the computation. The last thing that people are concerned about today, right, I have some issue with, is reproducibility. So here's a situation. When I run my computation in parallel, I can't guarantee I'm going to get the same result tomorrow if I do that same computation. So what I'm saying is I have a machine, and I have a problem. I'm going to run that problem on this machine, and if I come back tomorrow and run the same problem on the same machine, I may not get the same answer. I can't reproduce the result. And that comes about because of, in parallel, I can't guarantee how things are summed up. If I sum things up in a different order, I may not get the same, exact answer. I can get round off error, which will be different. Okay, now, I'm a numerical guy, and I know that those differences, I'm not going to worry about it, unless I have an ill-conditioned problem or unstable algorithm. And I may magnify those errors I make. So I may make my run today and tomorrow and get totally different results. Totally different. And I understand that as long as I understand the nature of my problem. Right? So the guys who are certifying nuclear reactors, they say, hey, I got to have the same results today and tomorrow. I can't be in a situation where you don't get the same results. And if you're debugging programs, maybe you do want to get the same results today and tomorrow, because that would be a nice thing. So you know where the problem is. So that becomes an issue. Now, how can we guarantee reproducibility? That may be at a cost. That may have to sequentialize computations at a certain point. But really, from the standpoint of getting exactly the same answer, I want an error bar, and I can generate those error bars. We know how to get errors. There's uncertainty quantification which comes into it for larger problems, which focuses on this aspect. So perhaps we shouldn't be too concerned about that. So those are the problems I'm concerned about. Let me just drive, I've got, 5 minutes at least? Yeah. Okay, let me just drive a little bit into this. So fork join parallelism, we're developing a numerical library. We've developed a few of them in the past. Think of LAPACK. LAPACK is a package of software for dense matrix problems, systems of equations, least squares problems, singular value decomposition, eigenvalue problems. And it's driven, in some sense, by a fork join model. So it runs on a parallel machine, shared memory machines, it runs fine. And the way it runs parallelism is by this fork join model. So I come here and I have the opportunity to do something in parallel, and in the BLAS, I split the operation across encapsulating the parallelism within the BLAS and getting access to those multi-core systems. And that works fine up to a point. But when you're faced with thousands, hundreds of thousands, billion-way parallelism, you can't do that. So today we're looking at a task-based parallelism model within our software. Task-based parallelism, we're going to divide things up into smaller tasks, smaller chunks, and we're going to look at developing those things in the sense of generating tasks and putting them into a queue, and then having another mechanism execute those tasks in the queue based on the dependencies that have been satisfied. So we're basically generating a directed acyclic graph for the computation. And then we execute that DAG on the underlying parallel machine. It gives a computation which is more asynchronous and something which avoids that fork join bottleneck that we have. The other thing that's important is we have to lay the data out correctly. In a matrix computation, traditionally we would lay it out, if we were dealing with Fortran column-wise, we have to lay data out in tiles, the size at which we're going to do work on those things. we lay it out contiguously so we get easy access to that data. And we can then reference things very quickly. So we end up with a model for our numerical libraries today, which is being based on this directed acyclic graph approach, the DAG approach to it. It sort of has this explicit parallelism, it has implicit communication, it does fine granular tasks, it does things in an out-of-order sequence, basically executing this DAG, generating tasks, and then executing those tasks. The cartoon here says if I do things based on a fork join model, I end up with I'm looking at 16 cores executing, and I think about how that would be done on a fork join model. I would have things going sequentially, and then I would split things up running in parallel, and then they would come back together sequentially and split things up in parallel. And you end up with that kind of sequence. So time is running here, colored blocks are things which represent active work, and we get a lot of gaps here. So I don't like the white spaces here. A DAG-based approach allows one to squeeze out a lot of that wasted idle time and provide something which was much more efficient in terms of the overall execution of our programs. So we're designing the next package, a replacement for LAPACK, again, dense matrix computations, around this structure, hopefully to be able to take us forward to that large number of things. So this is a cartoon again about a run that was made on a 48-core system. This was doing a QR factorization of a matrix, and again you see very compressed execution flow. Again, there are 48 cores here, and time is running along this axis. Again, very dynamic, out-of-order kind of execution taking place, fine-grained tasks operating on these independent blocks, giving a very much more efficient operation. In many of our computations, we have components which have to be put together. So I think about, in this case here, I want to invert a positive definite matrix. I'm about to do something. I need the explicit inverse of this positive definite matrix. And the computation proceeds by calling three routines. It calls a factorization routine. It calls a routine which inverts a triangle of the matrix. And then it calls a routine which basically multiplies two triangles together. That's sort of the sequence. Three independent pieces. I can do those things independently, write them down as DAGs, and they look something like this. And they have execution flows which look something like this. Now, it's not bad execution flows, but again, there's a lot of white space between them. What I want to be able to do is to generate tasks for all those routines simultaneously. Think about generating all those tasks. Don't execute anything yet, just generate the tasks. Put them in a queue, and then start the execution on that pool of work that allows me to basically to press these things together to compress the computation even further, allowing one to define a DAG which has those three things sort of merged together and allows the execution to have a much tighter, much more efficient flow of execution based on that task-based DAG approach where we have knowledge of those three things composed into one. These DAGs can get very large. So, this is a DAG represented from a very small problem. This is, I forgot the exact size. It's a block size of 100 in this case, but it generates about 1 million tasks. I can't explicitly represent the DAG in this case. It's just too big to represent. So I have to come up with another mechanism for dealing with this. And within our library, we think about not generating the whole DAG, but generating a window. Oh, I hate this when this happens. So this is my backup software just started. And I can do this. So we generate a window on the DAG and start execution on that window. And as we execute that window's worth of DAG, we move on to the next window, basically sliding through the DAG, if you will, executing components until we finally execute them all. In a distributed sense, we want to go further. We don't want to explicitly have any part of the DAG. We want to parameterize the DAG. And we're working on a scheme which allows us to, instead of generating the DAG explicitly, even pieces of the DAG, generate a parameterized approach to the DAG. which would be much smaller in terms of its representation, allowing that representation to exist on each of the nodes within our parallel machine, allowing things to execute in a much more easy flow. So everything becomes much smaller because of that parameterization that takes place. So we have a software path, a tool chain, which basically says we're going to take the code that we generate with Plasma, which basically generates tasks. Each one of these calls to Quark here is a task generator. It generates tasks which have inputs and outputs. It takes that information, that code basically, and parses it and does an analysis of the syntax tree from that parse. And from that analysis, we can actually generate code which has the parameterized DAG in it. And that's the code that we're using on a distributed memory machine. So basically taking the Plasma code, which is designed for shared memory machines, running it on a distributed memory machine, which has the parameterization of that DAG, allowing for a very efficient operation. The runtime then uses that information, so we've designed a runtime to go along with that. The runtime uses that information to execute the DAG, to do the message passing associated with it, and do it in a way that lets us express the algorithm in a very shared memory way, but then execute it in a distributed memory way using this approach. And that's the replacement that we're currently investigating for our library. And it has very impressive performance things. Let me go to the conclusions here, as we are running out of time. Okay, reproducibility. We talked about that. Okay, so here's some conclusions. Okay, so for the past decade, we've invested and done things, and in some sense, we think about high performance computing. We focus on the hardware aspects of high performance computing. There's been a tremendous investment in the hardware side, but high performance computing is really an ecosystem. And that ecosystem is composed of not only the hardware, but software components that are along the way. The operating system, the compiler, it's composed of the algorithms, the applications, the numerical libraries, and we need to make an investment in all of those components in order to effectively advance on our way to Exascale. We can't just focus on the hardware in the absence of looking at new algorithms, in the absence of compiler technology, in the absence of new software libraries. And so that needs a better balance overall within the ecosystem in order to effectively have things move towards Exascale. And there's tremendous challenges there for the software in terms of the programming models, especially as we move to this level of parallel computing. So let me stop there and ask if there's any more, if there are any questions. I'd be happy to answer those questions.
Thanks, Jack. Questions? Yes, Nelson.
Yeah, so Jack, the trend we've seen for roughly 30 years is that floating point speeds are outpacing memory speeds, and the gap is getting wider. You've got figures of 200 to 500, that's what I see too, is what I read. There's a small group in the world that works on interval arithmetic, and one of them, Ulrich Kulisch, has argued for about 30 years now, we really need exact sums and exact dot products. The software implementations of these, if we can do the order of 500 flops every time we move a word in memory, perhaps we ought to be redesigning the cores of all of our algorithms to do just that. We'll get rid of this problem of non-reproducibility of parallelized sums, for example. What's your comment?
Sure. So interval arithmetic is a mechanism to give us solutions within a certain region.
Right, but he's arguing just we need these primitives that are independent of
Yes.
interval arithmetic.
That's right.
But will give us a guaranteed exact sum.
That's right.
Around.
That's right. And so now, so we're faced with the following challenge in that context. And the challenge is, how do we get manufacturers to think that this is an important problem? And how do we get manufacturers to make changes to their architecture to address this problem, where this problem is not their main business, right? So how do we get them to make perhaps radical changes, adding additional features to their thing for the scientific community? And if you take a look at what's happened to high-performance computing over the last 10 years, scientific computing is really focused on commodity processors. Commodity processors because they're so cheap. And the investment that's made in designing and the architecture and the research that goes into them can be spread across so many things, so many components that they sell, that it makes sense. They have them make a design that would affect just a small number of those things. I don't think it would make economic sense to the Intels of the world to make those changes.
Right.
So my guess is that's the reason why it hasn't happened.
But we could do it in software, because we've
We can
got
do
all
it in
these
software, that's
straightforward-
right. Absolutely. So then the question is, how efficient can it be done in software? What's the efficiency? Are you willing to put up with a slower, I'll assume that it's going to be slower than we do it today, and does that make sense for these large computations that people are thinking about doing? They may be able to do it for a small thing, but would they be able to, would they really want to make their computation 10 times slower to gain those attributes? And you know, my example of the guy who wants to turn off is just the opposite. So I would say I think it's a good thing to have the option to go that way, but I would say the reality is not many applications would
But it
engage
could
in
be a component of plasma, for
it
example.
could be a component plasma, that's right. To take that and to think about doing the floating point operations in that context. Yeah. Yes.
It seems to me the hardware people haven't done enough in one sense. They've done a lot for speed of floating point, but not enough for data transfer.
Yes.
I think they could do more in that respect.
Right. So the question really is, you know, there seems to be a tremendous gain that's happened in investment in the floating point operations, but not so much in the data movement. Maybe they should think about making their data paths wider, or doing something to enhance the data transfer within memory. That certainly would make sense for me. That's the main bottleneck for all scientific computations. So we would all benefit if we're doing scientific computations. But it probably doesn't benefit those other guys who make the most of these machines. So I would say, again, it's an argument that it's not going to be commercially, there's not a commercial motivation to have that move forward. But it does make sense to me to have that. You saw the numbers, though, for the power numbers. Again, everything going against the data movement. It's getting more expensive. And so, yes.
Many people have said that there are all sorts of things that you won't be able to do at exascale. But people have always said this at different times in the past about, oh, this will never happen, you'll never be able to do this. But while it's clear there are technology limits, do you think the same limits apply to ingenuity and inventiveness?
Right. So we're claiming the sky is falling at some level, and we've always claimed that perhaps, and we've always managed to get around it, and we've always managed to use whatever machine we've been given, and seem to use it quite effectively. Without big changes happening. So first off, there are some people who say the exascale machine, you can't build it. It's not going to work. The constraints we have on the problem are such that you cannot build it in this time frame for that price. So that we may not be able to build it, right? So we have a group of people saying that. Will we be effectively be able to use the machine? You know, it's been my experience. First off, there's not going to be many of these machines in 2020. There may be 2. Is the thinking. And if there's going to be a machine, it'll probably be placed at one of the weapons labs, just because they have the money and they have the perceived need for building those machines. My experience with those guys, they're going to go through heroic measures to implement their algorithms on this machine, and they will be able to make use of the machine. Whatever machine is there, they will embrace it. And they'll grind down, 20, 30 postdocs to get their applications implemented, and they will get results out. Yes, they will declare success. For the more common people to use such a machine, I would say that we need better programming features in the machine to effectively use it. You can just look at the way productivity has been enhanced by tools like MATLAB, which make it so easy to do things and to experiment and to get stuff. And the performance is not as great, but it enhances our productivity. And maybe that's something we should be focused on, not the machine's productivity in that context. So there's many sides to that story.
Okay, well, let's thank Jack for a really interesting talk.